Today's Jim. Oh, here, let's plug you in, Jim. Are you doing HDMI?
Yeah.
Okay. Let's see if this works. Okay. Well, here. Let's get your. There's the information, and welcome, Jim.
Thanks, Bartlett, and it's really a great joy to start off the proceedings for this great conference. So I'm going to start out just talking about some work that we've been doing in our lab the past couple of years, addressing issues about pattern separation and pattern completion. These are very classic theories about the hippocampus dating back a number of decades now, and they're the kind of theories that have been gaining lots of support. But we'll hear in the next talk, I think, some contrary viewpoints on that. So it should be an interesting way to start off the meeting. But we're going to talk about some new twists on some of these classic stories. I like to start out my talks always with this sentence, which comes from the very first page of O'Keefe and Adell's book, The Hippocampus as a Cognitive Map. This sentence is the one-sentence summary of the cognitive map theory. The hippocampus is the core of a neural memory system, providing an objective spatial framework within which the items and events of an organism's experience are located and interrelated. I like to do this sentence because when you hear about the cognitive map theory and you hear how people talk about it, and even how O'Keefe and Adell came to talk about it over the years, you often forget this second part of the sentence, as if it's only about spatial learning and spatial mapping. But this theory is an explicit theory of episodic memory. O'Keefe and Adell, at least as they originally intended it, the point of the spatial framework is not just to support navigation and spatial learning, but this is the framework that they thought the brain uses to organize and interrelate the items and events of experience in a way that all the different components of experience can be brought down, interrelated onto this spatial framework. We now think about it as a spatial temporal framework, and I think Mike Hasselman will be talking about that later on, and binds it together in a way that it can then be retrieved as an episodic memory. So how does that work? Well, here's a very, very simplified view of some anatomy that suggests that there are two different anatomical frameworks that come together into the hippocampus. They're interconnected with each other, but one framework coming to the medial entorhinal cortex we think belongs to that provides this spatial temporal framework, and another pathway coming to the lateral entorhinal cortex, the hypothesis goes, is what carries the representations of the items and events of experience. I'll bring this here now because this is all by background. I'm not going to talk about any of this in this talk, but I just want to put it in a bit of a bigger picture of how this is really becoming a consensus view of what the hippocampus is doing. So people like the late Howard Eichenbaum, who just passed away this year, unfortunately, but he was talking about along these lines as well as this is something that I think John O'Keefe and Bruce McNaught and a number of people would really have some agreement that something along this line is what's happening in the hippocampus and what its function is. But I'm going to talk today about this particular part of the circuit where the dentate gyrus CA3 get input from both of these streams and somehow combine together the information about the items and events of experience onto the spatial temporal framework to create memories. And the classic theories suggest that dentate gyrus performs a pattern separation operation, whereas CA3 is doing a pattern completion operation. And I'll define what we mean by these specifically. But that's what I'm going to talk about today, about these two regions. Evidence from our lab recently suggesting, like I said, some kind of new twists on these two stories. So what do we mean by pattern separation? It's a term you see over and over again in the literature these days. We talk about it based on David Marr's initial idea about expansionary coding. That was part of his cerebellar theory that he published in 1969, talking about the granule cell layer in the cerebellum. And then people like McNaughton and Rolls and Treves started talking about the dentate gyrus granules layer doing very similar operations. The idea is that if you have an input layer and you want to store it to minimize interference in that memories, the expansionary coding is that if you got like 3 out of 8 neurons, say, as the input pattern, if you represent that now in an output layer of a larger number of neurons, you might have maybe 3 out of 16 neurons being active. Well, how does that help memory? Well, let's assume your next input pattern is very similar to the first one, but by this expansion recoding hypothesis, you now make this representation much more different than this one than the inputs are. So that's what Mars suggested as a way of doing pattern separation, orthogonalization. And then if you store these representations with much less overlap, you'll have much fewer errors in recall and much less interference. You can store many more memories in a situation like this without interference. So as this idea was applied to dentate gyrus, it suggests that dentate gyrus granule cells should fire very sparsely. The fewer representations that each neuron is part of as a population code, you can also store more memory. And the prediction would be that they have very sharply tuned place fields in an environment, and they should fire rarely in a limited number of environments. So it's an explicit prediction of this idea that granule cells should fire in a very sparse manner. And there's been the whole history of recording from granule cells in the hippocampus in freely moving animals has actually been plagued by a problem. And the problem is as follows. There are actually two types of excitatory neurons in the dentate gyrus. You have the granule cell layer here. So this is the hippocampus dentate gyrus, CA3, CA1. You blow up this region around the dentate gyrus granule layer. The large majority of cells, huge majority, are adult-born, are granule cells that are born during development. But right here in this region called the hilus, there are these large cells called Mazi cells that are also an excitatory cell type. They feed back onto the granule layer and actually get feedback from CA3. And as well as in this population, we have a population of adult-born granule cells during adult neurogenesis. And the question is, if you put your recording extracellular electrode in here, you don't know which of these cell types you're recording from, as well as a population of interneurons in here, which I won't even describe. So I'm going to talk to you about our recordings where we've identified the properties of these Mazi cells, these gigantic cells just below the granule layer, and then the population that we believe of mature granule cells. We're trying to understand newborn granule cells, but we've got no data on that yet. So here's some studies that Doug Goodsmith and Kim Christian did. Kim works with Hong-Jung Song, our collaborator, where we put animals in 4 different environments and had them just do random spatial foraging tasks in these just completely separate rooms in our lab with different spatial cues around there. And we were very careful to make sure that we were only looking at data that came where we knew exactly where the tetrotip was, and that was clearly not in the granule cell layer. And these are recordings that were done, and we sacrificed the animal either that day or the very next day. So we knew that tetras hadn't moved a lot. So we as sure as we could be from extracellular recording techniques that we were recording cells in the hilus. And this is what the firing fields of these cells looked like. They fired, here's cell 1, and fired in all 4 of these different rooms in multiple patches within the room. And here's another example of this cell from this recording tip, fired also in all 4 rooms with very different spatial firing patterns in each room, as well as a patchy pattern in each room. Now it turns out that this was the pattern of activity that a very influential paper in 2007 from the Moser lab suggested was actually granule cells firing. And it really threw the field for a loop because nobody would call this a sparse pattern of activity. It seemed to suggest that granule cells were not doing what we all thought they were for decades, but based on very little real evidence from the recordings of these cells. And they suggested that this is what granule cells did. But do notice, though, that the firing patterns were different in each room, so there could still be a way of doing pattern separation or orthogonalization in this kind of a code. And this paper in 2007 suggested that dentate gyrus was still doing pattern separation, but by a very different method than Mars' original idea of expansionary coding, which required the sparse activity.
Just a question, quick question.
Yeah.
What exactly is represented in each one of these squares? I'm a little confused.
Okay, I'm sorry. All right, I'm assuming too much knowledge of your play cells. Okay. What's going on here is each of the
one cell or multiple?
Each of these is an activity of one well-isolated single unit, one cell. And the gray squiggles is the trajectory of the animal running around in each of these environments, A, B, C, D. And that's the gray squiggles is just the trajectory. The red is where the rat was when that cell fired.
Thank you. And it's one cell.
That's one cell, and that's another cell. This is all the activity of a single cell. Yeah.
And how big is the environment?
Maybe about 1.5 meters. The room's about maybe 9 feet square.
How does this compare with neurons in the granule layer?
Next slide.
Okay.
I'm sorry please, if I'm assuming too much, people know, stop me at any time. Okay. Here is what now when the tetrode is in the granule cell layer, this is what the activity looks like. 2 different cells here. Cell 2 was silent, except for 1 or 2 rare spikes in all 4 environments. Cell 1 fired with a very nice place field. This would be indistinguishable from a classic CA1 place field that O'Keefe and Dystrovsky discovered years ago, but was silent in the other 3 rooms. A little bit of a firing property here. And with the 2 examples I'm showing from here and the previous slide were actually very typical examples of what the recordings were like in the granule layer versus in the hilus. So this is what we always thought classically that granule cells should do. Very sparse coding. The cells don't fire much at all. In most environments, they're silent, but when they do fire, they fire in a single field in only 1 of the 4 environments. So these results are consistent with this expansionary coding idea that people have thought for a number of years. So here's some summary statistics on all this. If you look at all of our recordings from the granule cell layer, and Doug, we created some, I won't go into details, he created some classifier techniques to try to classify these cells based on a number of parameters, and we're pretty confident that these are accurate, but not 100% accurate. But what he classified as a granule cell recording, the number of active rooms, how many of those 4 rooms did a cell have activity and a place field? Cells in the granule cell layer, most of them fired in 0 rooms. They were just silent throughout the whole experiment. Maybe 1/3 of them fired in 1 out of the 4 rooms, but none of them fired in all 4 rooms. In contrast with the recordings from the hilus, most of these cells fired in all 4 rooms, occasionally 3 or 2. A couple of them didn't fire at all. These actually might have been misclassified cells. We don't know. If you look at how many place fields there were when the cell was active, did it fire in 1 spot in that environment or multiple patchy spots? Almost all the granule cells layer recordings had 0 place fields. On occasion, they had 1, whereas cells in the hilus had a distribution. The mode was around having 2 subfields in an environment, every so often 1 is 0, but sometimes up to 4 or 5 or more. So very clearly, very distinct populations of activities in these 2 cell types. Now, that's still extracellular recordings. And we don't really know exactly what these cells are. So Xiaojing Chen, a postdoc in the lab, did some juxtacellular recordings in freely moving animals. I won't get into details. This is almost like an intracellular recording, but not quite. But the idea is we can actually record the cell while the animal moves around and then fill it with neurobiotin to actually label the cell and find out exactly where it was. Here is some examples of 2 granule cells that she identified as being granule cells in the granule cell layer. Each one of them had a single firing field here in the center, here along the wall. Here you can actually see the fluorescence image. And all the granule cells that she had were like this. Most of them didn't fire at all, but when they did fire, they looked like this. And here's her one really good example of a Mazi cell here in the hilus. You can see it's called a Mazi cell because of the Mazi-like appearance of these so-called thorny excrescences, these postsynaptic large spines. And it was one of these cells that had actually 3 firing fields. So this is more evidence that really confirms the idea from the single unit recording about these 2 different cell types. So the interim summary is that the granule cells fire extremely sparsely in very few environments, displaying the single fields when they're active, consistent with what people had thought for a number of years about what granule cells should be doing. Mazi cells, though, this other type of excitatory cell in the dentate gyrus, they fire promiscuously in many environments, typically displaying multiple firing fields. And each cell can show what you might call pattern separation in terms of taking environments and creating very different representations of them, but they use distinct mechanisms.
I'm sorry, about number 2. Are you distinguishing Mazi cells from grid cells?
Mazi cells and grid cells are completely different. So grid cells are in the medial entorhinal cortex and other parts, but there are no grid cells in the hippocampus per se. Mazi cells are this cell type that's in the dentate gyrus. Okay, so
I understand, but they seem to behave like looks like a grid cell receptor.
Well,
it's a grid-looking thing.
By chance, when you look at these, they're patchy, but there is no, on average, there's no hexagonal regularity from them. Okay, so that's the point.
So the Mazi cells get their inputs from the granule cells? Is that how
They get inputs from granule cells, synapse onto Mazi cells,
and the feedback?
and they can feed back to granule cells. That anatomy is not exactly worked out, but the interesting thing, though, is the synapse from the granule cell onto the Mazi cell may well be the most powerful synapse in the brain. So Helen Sharpman has data in slices where she can record a granule cell and then record Mazi cells, and if she finds two of them that are connected to each other, she reports that every time this granule cell fires, it always produces an action potential in the Mazi cell. So it's really like a one-to-one synapse.
And how many cells is the granule cell output connected to, the axon connected to? How many cells versus the Mazi?
I know that the estimates are that a single Mazi cell will get input from around 200 granule cells. I have to think about the other way. I don't have those numbers on top of my head.
But is it less, or granule cell has less or more?
Less.
I mean, connects to less cells or more cells? Granule cells.
I guess I'm not sure the question.
How many connections are from a granule cell to other cells?
I don't really answer that. We believe, although I'm not sure, that may not be true, but our hypothesis is that each of these firing fields of these Mazi cells is the single firing field of one of its granule cell inputs. But I don't know the answer exactly to your question, and it's not clear whether those numbers that are out there are how accurate they are. Okay. Okay. So basically, that's the part of the story. So we think we have, rescued the classic theories that, not the theories, but the data that we thought granule cells fired appears to be actually the way they do fire. So I'm going to move on now to the second part of the story, this pattern completion part of the story. And what we mean by that is this is also coming from Marr's work. He called this collateral effect in his theory of the hippocampus. When you have cells that have these recurrent collateral system reminiscent of what's the CA3 anatomy in the hippocampus. And the idea is that you have an input pattern which drives this output pattern. Because the recurring collaterals, if these are modifiable synapses, you can actually modify these synapses such that the cells can actually, patterns here can do some auto-association and do things like pattern completion or error correction, such that if only a partial input pattern is presented to the network, because these recurrent collateral system, these cells fire, but because of these strengthened synapses here, they actually drive the activity of the remaining part of the system of the pattern, and that's what's called pattern completion. If I, instead of having 2 out of 4, I had put all 4 neurons here, but one of them was incorrect, like the input was wrong, similar networks with proper inhibition and so forth would do the same thing, would actually correct the input to do the output that would be expected. So these ideas of pattern completion or generalization, error correction, these kind of networks can, as far as I'm concerned, they're all pretty much different manifestations of the same properties. And the thought has always been, based on this, that's what CA3 does. That's sort of the classic theory. So we've been testing theories like that over the years, and we've done situations where we have an animal running around on a circular track with local cues on the track that are very salient, and standard distal cues on the wall. And if you look at an overhead view of this apparatus, here's this track with local cues that the rat just runs around in circles, basically going for little pieces of food on the track. And on the black curtain are an array of distal landmarks. And after the rat is very well familiar with the environment, one day we'll come in here and we'll do this. We'll rotate the track one way and the cues on the wall the other way. And we want to see, are the place fields controlled by the cues on the track or by the cues on the wall? And how does the system react to this rearrangement of the different landmarks, this mismatch between the two different reference frames, a local reference frame and a global reference frame? And here's an example that we published in 2004 by Ina Lee, where we recorded CA3 simultaneously with CA1. And we represented data the following. On the x-axis of these correlation matrices, we're plotting a linearized version of the rat's location in a standard session when the cues are in the normal location. So we just linearize the track from 0 to 360, and that's what's represented on the x-axis. The second standard session, after a mismatch session where we rotate the cues, is on this axis. And we just do a correlation. So basically, we look at all the population activity of all the cells recorded and correlate their activity between the standard 1 and standard 2. So basically, the cells that fire at this location here fire at the same location here. That's what's represented by this large correlation band on the main diagonal. Cells are fired here, fired at the same location, standard 2. Cells are fired here, fired at the same location here. It's just showing that, as expected, when the cues are in the same relationship, the hippocampal spatial representation in CA1 and CA3 are very stable. They have the same place fields in the same locations. Any question about these, how to interpret these? Okay. The interesting question, and it was completely expected by what we know about place cells. The interesting question is, how does a cell respond to these cue mismatches? Well, if we look at CA3 first, we see that there's still a band of high correlation. It's not as strong as standard 1 and standard 2, but there's still some band of high correlation there. Meaning, though, even though we've changed the cues, CA3 is taking this mismatched input, these incorrect inputs, and is still able to retrieve and show a representation that's very similar to the original one. But in CA1, without the recurring collateral system, it gets this input, but actually has very little correlation in its output pattern. So the difference between CA3 and CA1 we took as some evidence in favor of this idea that the recurring collaterals in CA3 were doing something that allowed CA3 to take this corrupted input and actually retrieve some version of the original input.
The band on the diagonal in CA3 for the standard 1, standard 2 is broader than that for CA1.
Yes.
Is it like that if you go standard 1, standard 2 without the mismatch?
It would be. The reason for this is that the place fields in CA3 tend to be a little bit larger than in CA1. So when you do these correlations, because each field is a little larger, it takes longer as you rotate them before the correlations go down to 0.
But it doesn't broaden because of the mismatch?
No, it's because it's just a property of the place fields themselves.
Is there any way to know which way the correction is being done, whether the animal is in fact using the distant cues or the nearby cues?
So in this case, the fact that this band of correlation is slightly below the main diagonal, that means that it's actually being being controlled by the local cues on the track, which actually was not what we were expecting based on the literature.
Correcting the signal from the more distant ones to match the local cues.
Yes, or for whatever reason, in this conflict between these reference frames, it's choosing to follow, quote, choosing the local frame.
So the ordinate, is that with respect to the distal cues, or the angle with respect to the distal cues, or with respect to the local cues? Or is this still same north-south orientation? So I'm wondering, I mean, you have an angle on the ordinate, but you have rotated the distal and the local cues in 2 different directions. So I'm wondering, sort of.
Right. So just to, had these cells been controlled by the global cues, this correlation band would have been now on this side of the diagonal. Okay. And when we record from medial terminal cortex, that's exactly what happens. The medial terminal cortex cells are controlled by the global cues. I'm not going to show that data, but we know that.
So why does CA1 not inherit the completed pattern? If it does not, what's the use? Because that's the
right. Let me get to the end of the talk, and I'll address that in a way that why we interpret that. Okay, if I get there. Okay, but great question, and I think we have an answer to it. Okay, so that experiment was done recordings in this part of CA3, where the recurrent collateral density is the strongest. What Hee-Kyung Lee and Chung Wang in the lab, the question here was, well, we actually know now from anatomy that there's a lot of differences along this so-called transverse axis of CA3. Recurrent collaterals are stronger here than here. This part of CC3 gets stronger input from the dentate gyrus and actually weaker input from the entorhinal cortex directly. So we wanted to look at differences along this axis. And the prediction was that pattern completion, or this effect, will be stronger out here where the recurrent collateral density is stronger than in here. And I'll go by this quickly because we've already seen these graphs before. This is our proximal CA3. This recording's from this part. This is intermediate CA3. This is distal CA3. In proximal CA3, intermediate CA3, and distal CA3, these are the standard 1 and standard 2 in which we did a 45-degree mismatch between them, a 90-degree, 135, or 180, different amounts of mismatch between them. But what you can see is when standard 1 versus standard 2, in all these cases, we see the nice band of correlation showing that the main representation and the standard sessions were intact, as expected. But what about the standard versus mismatch? If you look at intermediate CA3 and distal CA3 first, you see these bands of correlation that are still there. So this is replicating the effect we had published about in 2004. But in the proximal CA3, when it's a small mismatch, 45, you still see a band of correlation. It's weaker. But as the mismatches get larger and larger, the correlation bands go away. So we've done a lot of statistics to show, that this is real. And actually, this is exactly what our dentate gyrus recordings look like. So the proximal CA3 appears to be doing something similar to what the dentate gyrus is doing, and very different from what intermediate and distal CA3 are doing. We published this paper in the same issue of Knierim with the Moser lab, who had also very similar results in a different paradigm. So there seems to be, in CA3, functional heterogeneity along its axis. Proximal CA3 biased for pattern separation. Distal CA3 seems to be biased for pattern completion. So wrapping up here. So here's the last slide. So what's going on here? Well, the standard suggestions of trisynaptic circuitry from, say, the entorhinal cortex goes to dentate gyrus to CA3 to CA1, but it's much more complicated than that. The lateral medial entorhinal cortex project to all regions, mixed input to dentate CA3, but actually segregated inputs and medial entorhinal cortex to proximal CA1 and lateral to distal CA1. Dentate gyrus has stronger inputs, especially from the lower blade to the proximal CA3 than to the distal CA3. The proximal CA3 projects preferentially to distal part of CA1, whereas distal CA3 projects predominantly to proximal CA1. And there's also a higher density of recurrent collaterals in distal than proximal. So you put this all together, it appears that proximal CA3 is working more as a unit computationally with the dentate gyrus biased to do pattern separation, to make two input patterns more dissimilar. And that sends out to distal CA1, which is connected to this lateral entorhinal, this items and events pathway. Whereas distal CA3, it seems to be biased towards a pattern completion or generalization, error correction, and that actually sends to proximal CA1, which is part of this circuit with MEC where the grid cells are and the so-called spatial temporal framework. So I think there's some really interesting anatomy and physiology here suggesting that the computational models that assume that CA3 was all a homogeneous associative network, actually it's very different, that there are differences in anatomy and connectivity that suggest that there's something about what this region is processing wants pattern separated input bias, whereas this part is distal. To answer Xiaojing's question, why is CA1 ignoring the pattern completed input from CA3? We think that's because this is representing the local cues, but we know from other recordings that this is representing the global cues, and CA1 is getting a mismatched input, and just under our experimental conditions, it's saying, okay, my inputs are mismatched, my output's going to be mismatched because it doesn't have the kind of circuitry to do any kind of a judgment which is right. Functionally, you can make up a lot of stories about why that is. I'm not going to put too much evidence out. I don't think it's ignoring it, but it's just that's what it's doing. Okay, so I'm just going to finish there. Sorry I went a little over time with the question, but we had a lot of questions during the talk, so thank you.
We have time for maybe, are you want to get set up and get, oh, you are set up. Couple, any last question, or? I actually, Mark?
Yeah, so are there differences in the morphology of the CA3 neurons along that axis, or is the output of those neurons purely determined by the inputs they receive?
There are some interesting differences. No, work I know of that's not been published yet, so I'm not sure if I'm free to, from another lab, so I don't want to say too much about it. But no, people are finding gradients of different cell types along that axis as well, and different morphology of pyramidal cells. So some very good data will be coming out soon on that from another lab.
I can't resist making a comment here. What I really love about what you just showed is there's such a kind of a mismatch between the way that human beings would design a machine and the brain does, in the sense that, you know, who's ever heard of it? Like, we like to think of an area like CA3, but in fact, the properties, vary along the length of it. What does it mean to make a machine whose properties continuously vary, an information processing machine? I find that very, and then the connections have gradients. The whole thing is sort of not rectangular and partitioned, and it's a wonderful. We don't really have a way to think about architectures of this kind of design very well, so we're kind of struggling. But it's really important to remember that this is what's really there.
There's this whole dorsal ventral axis I'm even talking about, where and there's more data on that that's going on, but on the hippocampus. So it's a two-dimensional sheet, and things are mapped on each dimension, not unlike neocortex, where things are mapped onto these sheets, and some of the things going on here as well. And that's all interesting. So
anyway,
I think this.
Busy.
Yeah.
Thank you, Ken.